Just have a little distracting screen up there, I suppose. All right. Brittany, would you mind grabbing that door just so I'm not shouting out at the viewers? How's everybody doing? Good. Excited. A lunchtime stat seminar. That's good times. All right. So what I'm going to do today, work through some of the details of full information maximum likelihood estimation, which sounds super boring and dry, which might be, I don't know, there's some cool things. When I was going through and learning SEM stuff like that, when I figured out exactly how these models were estimating, it kind of clicked for me to help me go through and start to think when I'm running into a problem with different models or things aren't fitting the way that I want them to. I'm like, oh, this is kind of how this all fits together. So I think a useful and important thing. These are really excellent and great types of analyses to go through and run. Problem is there's lots of stuff that can go wrong with them, and you get errors and things will come up weird. And so just knowing how these models are estimated and thinking about how we use this information to interpret and infer things from our different models can be kind of useful with stuff. So this won't allow you, by the time we finish up today, you won't be able to go through and like run these models necessarily, but it should give you enough to go through and be able to go through and critically evaluate stuff that's going on. So we're going to talk about real quick review. There we go. OLS regression. Then talk about full information maximum likelihood, kind of talk about what's going on with that. We'll go through kind of a walkthrough, kind of a demo of what this would look like, what the estimator is actually doing, and then we'll finish up with some stuff on global fit. Okay, so starting out with our ordinary least squares. This is all review to everybody in the room here. But again, when we're going through and we're running a typical regression, we're typically running this with an OLS solution. Okay. Here I've got just some sample data from one of my intro site classes. Here's their first quiz. There's their midterm. Very clearly, there's an association going on right there, right? So down here, the midterm. So we're predicting our outcome. Our outcome is our midterm score. And here's our regression equation in our bivariate regression model. So we've got our intercept, our slope for quiz 1 here. Okay. So when we're going through and we're estimating things with OLS, what we'll see is the values that we get, the estimates that I get for my intercept and my slope coefficients here are going to derive directly from my residuals. All right. Here, if I go through and remember, sort of my residual is just going to be my observed value minus my predicted value based on my regression model. So some cases we're going to get pretty close. We're going to do pretty good. My model does a good job of predicting what this score should be for this given person. Sometimes we're going to have bigger residuals. So if I'm looking at sort of this case, you know, I've got a fairly large residual here. We really underestimated this person's performance. On the other hand, we really overestimated this person's performance. Okay, so what we're trying to do with ordinary least squares is we're trying to minimize the sum of my squared residuals for all cases in this set. All right, what we want to do is we want to find values for my intercept and my slope that minimizes the sum of the squared distances of all these cases from their predicted values. Okay, just bring up so people are kind of remembering this piece of things. Okay. So my solution here that we would go through and we would use to minimize the sum of the squared residuals here, we talk about this as a loss function, okay? And what we're trying to do is we're trying to minimize the sum of the squared residuals here. My residual again is my y minus y hat. But we know that y hat is equal to a plus b times quiz 1. We can substitute my equation right here for my predicted value, so that I go through and I have A and B individually within this system of equations. What I would go through, use some linear algebra to go through and derive sort of my values best fit for my slope function here. Again, as I start to get, so we hit a point, a minimum of that function where it's going to minimize the sum of the squared residuals here. Okay, but the main thing to go through and remember that with our OLS regression, values for A and B, just a straight function of our mean, variance, covariance, our sample statistics. Okay, we solve for this stuff directly within OLS. Okay, it's a complicated system of equations, but there's one answer. There's only one answer. We just plug it into the equations and we get kind of what we've got going on with OLS. Okay. Questions about OLS, what we're trying to do with this approach to estimating our regression coefficients. Okay. So what we're doing with full information maximum likelihood is a little bit different. Okay. OLS is great. OLS is fantastic. OLS is kind of our workhorse for all of our most of our regression models. But as we start to get into more complex systems and models and things along those lines, that OLS approach starts to fall apart, right? With OLS, we just have one outcome that we're trying to predict. A lot of times with our more complex models, we've got lots of different outcomes. And sometimes outcomes are predictors and sometimes outcomes are outcomes all in the same model. And so we need to sort of go through and think about a different way to go through and start to estimate to get our coefficients. And so what we'll see in things like structural equation modeling, certain types of factor analysis, multi-level models, mixture models, logistic regression, even some multiple regression, we'll start using maximum likelihood estimators. Okay, OLS works great for estimation or for multiple regression, but so does maximum likelihood. A lot of reasons where you and the folks who do put out M+ have a whole textbook on regression in M+. A lot of cool things that you can do with that, a lot of flexibility that you can go through and incorporate there. Okay. So some of the benefits of our full information methods, what these are doing are some of the characteristics. What we're doing, instead of solving for your coefficients directly based on summary statistics in your data, what we're doing is we're taking an iterative approach to the estimation of your model, right? So what maximum likelihood is going to do is it's going to set an initial set of coefficients for your stuff. It's going to test those, and then based on that test, it's going to tweak them. And then it's going to do it again, and it's going to do it again, and it's going to do it again until our model converges and we get something we say, okay, these are acceptable solutions. So a very different process than what we're doing in maximum likelihood, where we just plug things in and we get an outcome. Here, this is a more data intensive process where we're iteratively going through and refining these estimates until we get something that hits some preset criteria. But what this does is it allows us to simultaneously estimate a lot of different parameters in our model. If we look at this model right here, we're not going to get into latent SEMs so much today. That's kind of what this is, but there's a lot of different parameters here that we're going through and doing. Even if we think about a simple path model, or not a simple path model, just say, look, with just observed variables, we can do that in regression. And those path models that we used to go through with a series of regression equations and go through, and you can estimate a path model in OLS regression. This is essentially what process is doing. It's just using regression to go through and run a system of equations to go through and get what you would with those conditional and direct effects models. That's just using a regression approach. It just automates it, right? You used to have to know what you were about and have to go through and know what models to run and sort of how to put them all together. Process streamlines that. But what we can do, and the nice thing about maximum likelihood estimation, is we can go through and just run all this stuff all together, okay? Which is a nice piece of things. We can also go through with this, start to get fit indices to tell us whether or not our assumed pattern of associations in our assumed model, how well it actually fits the data. We can't get that with OLS regression. Also nice because there are different versions of maximum likelihood and different full information estimators that will account for non-normality, account for categorical data, like all the stuff that's a giant pain in the ass for us when we're trying to run through things in a regression model. Really easy, right? So now I don't have to worry about transforming anything, or, I mean, you still want to go through and screen your data and sort of take a look and make sure that you know what's going on, but methods that will go through and accommodate some of the stuff that used to make our life really difficult in terms of estimating some of these models. And then probably the biggest thing is that these methods can go through and account for cases where we've got incomplete data. This is a situation where running your multiple regression model in maximum likelihood might be a nice thing to do if you've got missingness in that set. It allows you to keep everybody in your analysis. Now I've asterisked this a couple of things. One thing you'll hear in sort of these models, you hear about people making the distinction between exogenous and endogenous variables. Does anybody know what the difference between an exogenous and an endogenous variable is? And exogenous variable just means that it's something that's not predicted by anything. Okay, so if I have regression model, something like that. Okay, so mediation model where I've got a couple of predictors. This here is an exogenous variable. Nothing predicts that. That just is. That's just something that happens in the universe. There's nothing that goes through and predicts that. These are all endogenous variables. Those are going to be outcomes. Now, outcomes in this case, these variables are sometimes going to be outcomes. Sometimes these are going to be predictors, but they're all variables that have something that's predicting that, right? Now, if I go through and I'm missing data or I'm missing values in cases for these endogenous variables, maximum likelihood will account for that. It'll go through and sort of keep those in my analyses. If I'm missing values for my exogenous variable here, those still get kicked out because there's no way to estimate that. There's nothing to predict that, right? So if I'm missing, if in my data set, I'm missing a bunch of values for this variable, and then I'm pretty good over there, you're not going to get much because those cases that are missing exogenous values are going to be all not included. But anything here, if I'm missing variable or values out here, this is a nice way to go through. Maybe I went through and I had, didn't start collecting some of these variables until later in a study or something like that. I can go through and still run this and can use the full set so long as my missingness is in my endogenous variable. Yeah.
So you described like those two center endogenous variables as predictors. Is your exogenous variable then always a predictor as well?
Your exogenous will always be a predictor. There's nothing that predicts that. That just is. And it starts when we start to get into estimation and path models and how we go through estimating errors and residuals and stuff. Like there's no residual for this because it just is. The variability is just the variability. Here, anything that's not predicted by our model is determined error, and we model that. Yeah.
And then also like those endogenous variables that are also predictors, are they also exogenous or okay, so they're just endogenous?
They're just endogenous, yeah. Because they are in this series of in this part of the model, they're predictors, but they're still endogenous because this is so we'll generally account for missing this. Other thing too, maximum likelihood will give us unbiased estimators or our parameters so long as our missingness in our model is missing at random, at minimum. Okay. If we have bias in our missingness, if our missingness in our data is not at random, you can still run it, but your parameters are going to be biased, right? There's nothing in this, there's nothing magical about maximum likelihood that fixes missingness, it just accounts for it. And so if I have, only people who are high on some variable that's not included in my model, right? There's systematic missingness going on, and that systematic missingness isn't something that's being accounted for in my model. What I'm going to get is problematic. I'll still get estimates. I just can't trust those estimates because I've got a problem with missingness in my data. But in general, and I've thoughts and feelings on, particularly for clinical people, about how we do this and ignore this, but it's what we do. But sort of knowing that maximum likelihood accounts for missingness, produces unbiased parameters so long as your missingness is at least, it's missing completely at random or missing at random. Questions about this? All right. So we're pretty happy about this. This is a good deal. It gives us a new tool that will go through and account for a lot of the stuff that we run into that just kind of turns into a pain and limits some of our standard analyses with our regression. Okay. So basic procedures with our maximum likelihood estimator. What we're trying to do is we're trying to establish parameters for our model that maximize the likelihood of obtaining associations that we're seeing in our actual data. Okay, so we've gone through and we've got actual data. What we're trying to do is set parameters for this model that maximize the likelihood of seeing the data that we're seeing. Okay, and what we do with these analyses is we determine the adequacy of our solution by comparing our observed variance covariance matrix with our model implied variance covariance matrix. We're going to be working with correlations today just because they're easier to work with. What is going on with these are always working with variance covariance matrices. What we're trying to do is we're saying, okay, here's the covariance matrix that we've obtained. Here's the covariance matrix that's implied by our model. What we're going to do is we're going to compare these two to see how well they map onto one another. So let's say we have this simple pattern model, just observed variables here. We've got 3 covariances estimated here and 4 paths. Okay, and what we've done here is we've made a very specific assumption about how these variables relate to one another. We're seeing that U relates to Y, V relates to Y directly, but U and V are associated with Z only indirectly through Y and some other stuff, right? X directly impacts Z, but X doesn't directly impact Y. V doesn't directly impact Z. We've got a system of implied associations here to say something very specific about this network of variables, okay? And so what we've got here is we've got our observed variance covariance matrix, right? This is just, we'll call this C, right? And you can think about this as just a correlation matrix. We've got covariances on the, or variances on the diagonal, covariances on the off diagonal here. Okay. So this is the data that we're working with, okay? This is our criterion, but with the way we've set up our model and the way we start to go through and apply estimates, those estimates are going to imply some very specific ways in which these data are connected to one another. And what we're going to do is once we go through and get our estimates for our model, we're going to compare this with this and see how well those two match up. And that's going to determine the fit of our model, whether or not our model is any good. Okay. So with maximum likelihood, what we're going to do is we're going to start with an initial set of coefficients. These are often random numbers, okay? These are randomly generated values for all of my parameters in my model, okay? Then what I'm going to do is I'm going to look at the associations that are implied by those parameters, and I'm going to go through and I'm going to compare it against what I actually saw, okay? Then what the model is going to do is it's going to go back through and start adjusting those coefficients. Going to make some adjustments and then again go through and compare against what we've got. It's going to iteratively do this over and over and over again until we get to a point where sort of tweaks to those coefficients are having a minimal impact on the overall fit. This is where we would say our model is converged. Okay. Now, usually you'll have a set of trials that you'll say, oh, it has to converge by this point. If it doesn't converge by this point, you can go through and up the number of trials. Hopefully, if you've got a good fitting model with reasonable data, it'll fit. Sometimes if you've got a really complicated model, you have to up the number of iterations before it'll achieve fit. But what you're wanting to do is those models to converge to where it's saying that we can no longer tweak these coefficients anymore and get sort of meaningful increases. We kind of hit a plateau. Questions about kind of this process, what this maximum likelihood estimator is doing. So it's different than our OLS, right? OLS, we just say, what's the mean, variance, covariance, and we just go through and these are the answers, right? This is the one solution that we've got. Here, what we're doing is we're starting with a bunch of random estimates and going through and iteratively improving on those until we hit convergence. Yeah.
So just like for clarification, with like that picture of the model, like those like blue or black lines, are those like are observed, whereas those green ones are like are predicted?
No,
or...
these green ones, these are covariances. These are just saying that these variables are correlated for some reason that the model doesn't know or care about, right? They just are correlated the way they are correlated. These blue paths, though, that's saying, I mean, anytime we're running a path model, we're implying causality, right? We don't ever say that, but that's for sure what's happening in terms of our model. I'm saying that U causes Y, V causes Y, X causes Z, but the only reason that X and Y are related is because of some of these different paths here.
This reminds me of like a permutation test or like bootstrapping procedure. So I was wondering if there's a replacement in the resampling or in the different iterations.
No resampling or no bootstrapping stuff. You can incorporate bootstrapping stuff where basically you just do this, but then you just do it over and over and over again for bootstrap samples, but that's a little bit different. Here we're just sort of throwing out some initial numbers, testing it, making an adjustment, testing it again. Basically, it's functionally a trial and error system, right? But it's just a really sophisticated trial and error system that works pretty good. Questions? All right. So some basic concepts with these types of estimators. One, think about our statistical model. Statistical model, this is just our set of equations used to test very specific theory-driven associations that are intended to describe some phenomena out there in the world. We're seeing something out in the universe and we're saying, this is how we think this operates. These are the things that we think influences that drive this stuff. And I'm going to set up my model that's, I think, is not a perfect representation. And my model is a simplification of reality. It's never an exact literal test of what all is going into it. It's just saying, in general, this is my heuristic in terms of how these things relate to one another, okay? And so we go through and set this up, right? And so our goal is never to find a model that fits the data, right? We do that, right? And that's important, but that should never be the goal, right? Because there are a bunch of different models. They're all gonna fit the data, sometimes equally. Some are functionally mathematically equivalent, but some of them aren't gonna make any sense. So just because you found a model that fits doesn't really tell you anything about it. Tells you that your theory is plausible, but it doesn't rule out other options that may even do a better job of accounting for what's going on, right? So remember that anytime we set up and specify a model, we're saying this is very specifically how these variables relate to one another. And then in the back end, if we go through and start screwing around with that model, that's when we start to get into problems, because then we're probably just capitalizing on unique aspects of the data set, right? What we'll see is some people will go through, have a model back. Here's my model. I'm calling my shot. Well, that doesn't work. So I jack around with it a whole bunch and then claim what I've found is the reality. This is what happens in the universe. This is how it all fits together. Well, no, this is probably just how your data fits together, how we can tweak this to make it fit the data that you've got. But there's nothing in there that would suggest that's a generalizable model that's going to fit if you were to replicate and pull this up again. Okay. So model fit is good, but it's not the end all be all. It's actually not even what we're really trying to do. We just hope that if we say, here's my model, this is how I expect things to work together, that if I go through and run that, it's more informative if it's just not a terrible model. If it just doesn't say, no, that's pretty wrong, then it's good. If it tells me it's good, that's awesome, but it doesn't tell me as much as I would like it to tell me with this. Okay. And other thing we need to think about when we're thinking about estimating these models, think about the amount of available information that we have in a data set. And the amount of available information that we have in the set is given as the number of elements in my matrix C, okay? This is my observed data. And we can calculate this very easily. This is just gonna be the number of predictors or the number of variables that I have in my model times the number of variables plus 1 divided by 2 gives me, this is all the information that we can go through and work with, okay? So in this example that we've got 5 variables here, right? So if we go 5 times 5 plus 1 divided by 2, it's 15, right? And if we go through and we count up the individual elements, we get 15 elements here, okay? This is all the information that we have to work with. Think about this as bits of information that we have at our disposal to go through and play with. Okay? Then we need to think about degrees of freedom. Okay, degrees of freedom with maximum likelihood estimation is going to be the number of elements in our matrix C minus the number of estimated parameters that we're proposing to estimate. Okay, so if I've got 15 pieces of information, there's only so many things that I can estimate with this model. Okay, and so here, the more degrees of freedom within SEM. degrees of freedom are kind of a weird abstract construct. Here, when we get into SEM, they're very specific. They tell us how many unknowns do we have in our model, right? And the more unknowns that we have, the more degrees of freedom that we have to go through and play around and sort of work with stuff. Or excuse me, the more degrees of freedom that we have, so the more constraints that we have on our model. There's more unknowns going on in terms of what we're looking at. Okay, so if we go through and we take a look back at our model here, okay, we've got 15 pieces of information that we can go through and estimate in this model. We don't need to get into the specification of sort of what this is looking at. You can just kind of trust me with this. We've got our 3 covariances here that we've labeled, so we need to have numbers for them, right? And then we've got 4 paths that we need to get numbers for. But then there's kind of the background stuff that we would also get. We have 3 variances for these exogenous variables. We need to estimate the variances of those, right? And then we've got 2 disturbances for our 2 endogenous variables. We've got little error terms that sit on top of those that we need to go through and estimate for those, okay? And this is just kind of what's going on with path models in SEM. So what we end up with is we got 15 pieces of information to work with, and we've got 12 parameters, okay? So here we've got a model with 3 degrees of freedom. People kind of seeing how that's working out, how we calculated that. Okay, so we've got 3 unknowns. All right, what are the unknowns in this? What do we not have direct connections to in this model?
X with Y.
X and Y, right? X and Y, we don't have a path for that, right? So that's something that we haven't gone through and estimated directly. So there's something there, right? Same thing, V and Z, U and Z, there's no direct connection with there. My model is saying that these things, now in my observed data, there's a correlation between those variables, right? Well, what my model is saying, the only reason that those 2 things are related is indirectly through other stuff, okay? And so that's what we're gonna go through and test with this. So here in the model that we've got 3 degrees of freedom, okay? But let's say CJ's got this, CJ doesn't like this. He's like, well, I think, boy, that X or that B should be directly related to Z, that U should be directly related to Z, and X should be directly related to Y, right? So if we go through, okay, sorry about that. So we would call this, when we got 3 degrees of freedom, we've got an over-identified model, right? It means that we have more information than we have parameters that we're going through and estimating. Let's say we go through and we add in all the paths that CJ wanted to have in there, okay? If we do that, we can go through. Now we've got 7 paths. Number of covariances, variances, and disturbances are all the same. We've just added 3 paths to our model, okay? So now we've got 15 pieces of information. We've got 15 parameters. We've got 0 degrees of freedom. This is fine. We can still estimate estimate this model. And what we'll do with this model will perfectly replicate the data that we've observed, okay? Now that doesn't mean that it's a great model. It just means that that's by definition what will happen. If I have a model with 0 degrees of freedom, I would call this a just identified model. And just identified models, this is basically running your process model, okay? It doesn't give you an estimate of model fit, because the model fit is perfect. Not because the model is perfect, it's just because mathematically this is what's going on with this, right? And so we can go through and we can estimate just identified models. The issue is that you won't get an index of model fit because you've got no degrees of freedom. Okay. So here's our just identified model, but let's say that Brittany says, well, what I also think that in addition to just being related, that the B connects to U directly, that B actually, an element of B causes U, right? And so Brittany tries to go through and throw in an additional path. Now we've got 8 paths. Now we're trying to estimate 16 parameters. We've only got 15 pieces of information. I've got negative degrees of freedom. And so what I have now is an under-identified model. This is a no-no. Can't do that. It won't give me a solution. I'll get an error with this, okay? Now, there are other reasons that you can go through and have under-identified models other than just running out of pieces of information. That gets into some more complicated stuff with specification of SEMs. But in general, for just looking at things basic concept is thinking about how many pieces of information do I have? How many things do I want to estimate? Am I going to have a model with positive degrees of freedom so that I can go through and actually get fit indices for this? Or am I going to have a just identified model where I get estimates for everything? I just don't know if the specific model that I've specified is any good because it's just going to perfectly represent my observed data. All right. So let's switch back to our over-identified model. So we're back to our over-identified model. We've got 3 degrees of freedom here. What we can do with this is we can start to see and generate, if we start to throw path coefficients in here, we can start to see what our model implied matrix is going to look like. And we can do this old school by going through and working through some tracing rules. The math on this is complicated, but we can go through with a little bit of effort, start looking at our model and start to determine and see how these estimates are going to start to imply things about this covariance matrix here. Okay, so we've got some rules for tracing our paths. No passing through the same variable twice, so we can't loop through stuff. Okay, after we move forward on a path, we can't move backwards, and we can only use one covariance, only one curved arrow in any path. Okay, so if I wanted to go through and see the relation between, let's say, U and Z, okay, main one, I can go through and I can say, well, this coefficient times this coefficient gets me to Z. Okay, this is basically, if you think about mediation models, this is essentially this is my indirect path here. Okay. Any other paths that people can see to get from U to Z? You see, Mesa?
VYZ?
Yeah, I can go, so to here, I can go B and this, so the product of B times F, I can do that, that gets me there. Anybody see any other paths?
AEG.
Yep, I go AEG, cool, all right. Can I go ACZ? Nope, that's 2 curved arrows, so you can't do that, right? Can I go here, back up there? Nope, I'm going backwards, right? So what we can do, start looking at this, what we can do with these tracing rules is we can start to put together, based on our coefficients, what our model implied associations are going to be, okay? So let's say I want to go through and look at all possible traces, and these are numbered, not lettered, but let's say 1, 2, 3, 4, 5, right? So this is U, Y, okay, here, right? We got 2 paths here. We've got D, and then we've got AE, which gets us there. Okay. So if I take whatever I got here and add it by the product of AE, that's going to give me my model implied correlation for UY. Same thing for UV, just here, just got 1 path, it's just that, right? Because I can't go here and then go backwards, that's illegal. I can't go here, then that's backwards, right? There's no direct path. So A is the only path that I've got the tracing for that. For XZ, okay? I've got the direct path here, like that. Then I can go CEG, and then I can go BDG and get there. Once I'm that, then now I'm out of paths, right? So what my model implied correlation or my model implied association between X and Z is going to be the sum of F plus this will give me my model implied association there. Okay. So what starts to become important when you start looking at this is my model says very specific things about how these variables can be related to one another. X can only be related to Y indirectly through other stuff, right? And if I'm going indirectly through other stuff, I'm having to multiply things. And if I'm multiplying decimals, what happens to the product of those decimals? They start to get pretty small really quick, right? So if X holds a stronger relation with Y, is my model going to be a good fit? Probably not, right? Because X can only get through Y through other stuff. And as I start multiplying that other stuff, that product is going to get really small. People getting the basic concept of these tracing rules? Okay, so let's go through, and just as an example, okay? So here's our model, and I've set up just a correlation matrix here that we can go through and kind of play around with. What we're saying here, because these are correlations, variances are all ones on the diagonal, okay? Anything that's a direct path, I've set at a correlation 0.5. I've set covariances at 0.3, and then we're saying U to Z, B to Z is both 0.5, or excuse me, 0.25, and then X to Y, we're saying is 0.13. Okay. So I go through and I went through and I set my estimates for each one of these parameters just equal to sort of correlations in this matrix, right? Just to put something in there. Okay. If we go down through and we start working through our tracings, okay. Correlation of U and V is easy. V and X, U and X, the only way these things can be related is through that covariance. And so these are all pretty easy and straightforward. Okay. Then let's say I want to look at the relation between U and Y. Okay. Well, I've got a couple of different tracings that I can get there. I can go directly through D, right? Which is going to give me a value of 0.5. And then I can go AE, right? Well, that's implying this 0.3 times this 0.5. We multiply those and we get an expected correlation between U and Y equal to 0.65. See how we got that? Okay. I'm looking at UZ. Actually, 3 paths that I can get there. None of them are direct, right? But I can go directly down the line. I can go D times G. I can go A, E, G, and then I can go B times F, right? I go through, add those up, and I get a model implied correlation of 0.48. Okay. And then we can keep doing this for all of the different paths that we have on here, right? And so what we get, based on this model, and based on the estimates that I have for these paths, what I can do is actually construct a model implied correlation matrix. If these are the answers, if these are the actual paths, this is what I should see in terms of associations between these variables, okay? So if I go through and I compare this to this, I see I've perfectly captured all my covariances, right? Those are all good. But everything else, it looks like I've overestimated and summed it quite a bit, right? I've about doubled these two. I'm 0.15 over on these, all of my 0.5s. This correlation I've about doubled, right? So what the maximum likelihood is going to do is it's going to look at the difference between this, and then it's going to start to make adjustments to your coefficients to try and bring this in line with this, right? So some things are going to increase, some things are going to decrease. It's going to run through that and sort of try it again. Now, the problem is that sometimes what I've done is I've specified a model that doesn't do a good job of accounting for how these variables are related to one another, okay? So let's say I change this up and I say that Z is functionally unrelated to U and V. I'm saying that these two variables have almost nothing to do with Z here, but X and Y are strongly related to one another. That's the data that I'm seeing, right? Now, all of a sudden, the fact that I don't have a direct path here is really screwing up my model, right? It's going to be hard. What the system is going to try to do, how can I strengthen the model implied association between X and Y in this model? I can start making these other coefficients larger, right? Implying that they're more strongly related than they are. But I've already overestimated those. And if I start making those bigger, I might sort of improve this, but everything else is going to get a lot worse, right? Same thing here. I've wildly overestimated the relation between these variables, right? I can start pulling these things down, which will maybe sort of fix some stuff. But still, with as strong as these other paths are, it's gonna make it hard to get these paths down to sort of something there. Right? Same thing if we go through. Batteries. All right, let's say now I'm saying X and Y are functionally unrelated, but sort of these two are still strong, right? Basically, what the estimator is trying to do is it's trying to get all these sort of adjusted, put together so that it fits everything. But if I change one thing, changes everything else in the model. Okay, an important concept to be thinking about in terms of these types of models. If I change one thing, has radiating impacts on everything. Everything else has to change anytime I change one thing. So yeah, like whack-a-mole. That guy's probably gonna kill this game. You got some sweet cargo shorts, so. Awesome with there. So some practical implications of these types of analyses, okay? Larger models are gonna be easier to fit than smaller models. If I've got larger models, got more variables, there's just more stuff to account for, right? So here I've got my basic mediation model. That's gonna be a lot easier to fit than something like this. There's just a lot more things to go through and account for. Okay, if you're thinking about doing like CFA types of measurement models, if I'm trying to get a measurement model on a measure with 7 indicators, and I'm like, yeah, my CFA is a good fit. Well, it's probably almost for sure going to be a good fit because you don't have a whole lot of indicators in there. If I got a measure with 50 items, that's going to be a whole lot harder to go through the bit. Okay. In general, models with more degrees of freedom are going to be more difficult to fit than those with less degrees of freedom. Okay. My model with more degrees of freedom, I'm going to say that's a more parsimonious model. It's more constrained. Okay. I'm saying I'm doing with my model with more degrees of freedom, I'm doing more with less. I'm saying I don't need, if I want to have a perfect model, I just predict that everything's going to be directly related to everything else. And then I'm going to have a great fitting model. It's just that's kind of a crappy model, right? Our model should synthesize the information that we're getting, right? And so for that more parsimonious model, there are more constraints on this, but means it's going to be harder to go through the fit. What people will find is that like, oh, hey, I found that this less constrained model with fewer degrees of freedom fits better with the more constrained model with more degrees of freedom. You didn't find anything. That's just how math works, right? That's exactly what should happen with this, right? So if we're looking at this CFA model versus this SEM model, the exploratory model lets everything relate to everything. That's going to fit really, really well, right? You shouldn't be excited if you get an ESEM that fits really well. This is a much more constrained model. It's saying the only reason that these variables are related to one another are indirectly through sort of these latent factors, right? This is a much, much harder model to fit than this, right? So if I go through and I start adding paths and it makes my model get better, that's just the way things work. That's kind of how what you would expect things to have here. Yeah. Misspecification. If I have a model and I haven't set it up correctly, and sort of the paths that I've proposed are not plausible, what's going to happen is that we'll see something called error propagation. We'll see the consequences of that misspecification get spread out through the whole model, right? All of a sudden, we'll have a covariance that's inordinately strong because I've not specified a direct path where a direct path needs to be there. The model's trying to account for that, and so it has to go through and impact other estimates to go through and try and get things up to speed. Okay, so anytime you're going through and taking a look, not just at your global model fit, you should look at that, find the very next thing that you should do is start looking at areas where your model is not fitting well. It starts looking at standardized residuals, things along those lines to say, hey, what's going on with this model? Why is it not fitting? Even if you have a good fitting model, go down through and take a look like what part of this model is it, what parts of this model are not working well. So here we got a big vector model, right? And this model is saying the only reason that my first indicator 1 is associated with indicator 4 is indirectly through this loading and then through this and then through that, right? So the only reason these two things should be related is through that stuff. Now, model or item 1 and item 4 hold a very strong direct relation with one another. this model is not going to do a good job of accounting for that because it's got to force and trying to recreate that correlation indirectly through other stuff. And so now what's going to happen is you're going to get a bunch of coefficients that are probably much stronger than they should be in order to try and make up for that. And so what ends up happening is that error starts to go through when maybe I just need a covariance, just linking those two together, and then that fixes whatever's going on. So long as that makes sense conceptually. Well-fitting models are not necessarily valid models, right? There are lots of different models that all fit your data the same, right? This is an issue in SEM that doesn't get talked about. We ignore this, talk about equivalent models. Just because you found a good fitting model, always need to go through and think about theoretically, does this make sense? It's a huge thing in PTSD research. People like get real worried about the factor structure of PTSD and like, oh, my 15 item model of P or my 15 factor model of PTSD fits the data wonderfully, Vic. I bet it does, right? Does anything that you've got actually sort of map onto some theoretical model of the construct, what's going on with stuff, right? So again, our goal should always be to find the most parsimonious model that does a reasonable job of accounting for things. Just because I've incrementally improved my fit by like a half a point on something doesn't necessarily mean that I've got a better model. Okay. Other things to think about in terms of running these types of analyses, bill scaling. Have to think about your model or your variables in your model. If I've got variables that are continuous but run on a 0 to 1 scale, and another variable in my model that runs from 0 to 100, my variances are hugely different on those. That can start to screw stuff up. It's easy to fix. You just got to go through and rescale things so that it all kind of falls on the same, similar-ish scale. So be aware of the scaling of your variables and kind of what's going on there. Also, collinearity. This will start to wreck your model. Okay. When you start looking at interaction terms or things along those lines, this is where some of those centering procedures start to become very, very valuable. If I don't center and I throw it in, like in the matrix algebra, I'm basically trying to divide by 0 and the whole model will crash down just because I've got crazy collinearity going between my variables. So OLS regression will handle this pretty extreme. I mean, you get problems with your estimates, but it'll screw up your maximum likelihood estimators pretty quick. All right. Okay, gonna finish up talking about just some basic indices of model fit. This will probably be review for most of you, and it's actually pretty straightforward. Model chi-square, this is your literal test of the difference between C and C prime. Okay, you'll always get a model chi-square. Your model chi-square is important because it serves as the basis for a lot of your other fit indices, right? And if you found that you had a model chi-square with a very, very large p-value, right? Saying that there's not a significant difference between C and C prime, that would be awesome. That would say that your model has done a good job of recreating your observed variances. Problem is anytime we're running an SEM and using maximum likelihood estimation, this is a large sample estimator, means that you should have lots and lots of people. If I have lots and lots of people, I've got lots and lots of power. And so even trivial differences will start to come up as significant or with associated with low p-values, right? So in general, because the chi-square is sensitive to sample size, in large samples, which is what you should be using, probably not looking at that model chi-square to make a determination on whether you've got a good, a well-fitting model or not, right? If it's associated with a large p-value, good for you, but it probably won't, particularly if you got a large degree of freedom model. So, but still important to go through and report this. Your chi-square is also going to be sensitive to large magnitude correlations in your data. If you got variables that are highly correlated with one another, that's a lot for that model to go through and account for. So there are different types of things that we'll go through and make this not a good standalone test in most cases, but always report your chi-square, report your degrees of freedom, because this is the basis for most of your other measures of fit. Your RMSEA, okay? RMSEA, this is a parsimony adjusted index. What we're doing here with this fit index is we're correcting for model complexity, right? So if I've got two models, right, One has similar fit and one is more complicated than the other one. The one that's less complicated is going to get a better value for this, just because more complex model is going to get penalized for being more complicated. Okay. So again, going back to this idea that we want the model that has, it's easy to fit a model if I throw 1,000 different parameters in there, right? The more parsimonious model is going to get preference with RMSEA.
Does that have implications for like how, like what we should expect to see in our MSEA between like an EFA and CFA, for example?
Yeah, I mean, those are kind of completely different models.
Yeah.
And so I would expect your ESEM is always going to fit way better than your CFA. So again, with all of this stuff, what you should be looking at, like, do I have a reasonable fit, right? And if you called your shot, you got reasonable fit, you're good, right? Look at localized strength to see if there's anything that's very much not being accounted for. But what happens is people like, oh, I get something, it looks fine, but then I got a grass and greener thing, like, I really like that to sort of kick up a half notch. So I start going through and doing a bunch of stuff that actually makes my model worse, even though it makes my data fit better, right? So always be thinking about practical implications there. Rules of thumb, less than 0.05, call this close fit. 0.05 to 0.8, reasonable error of approximation. Greater than 0.1 is probably not a great model. We also get, what's nice about RMSEA is we get confidence bounds, right? So if I've got an interval, and this is where we start to get in that gray area that we actually live in most of the time. If I've got a 90% confidence interval that includes 0.05, I wouldn't reject the null hypothesis that the actual value is less than or equal to 0.05. But if I also have an interval that captures 0.1, I can't reject the possibility that this is a garbage model as well, right? So wanting to go through and take a look at your point of estimate as well as your confidence bounds for this. Okay. RMSEA, good way to discriminate between good and really good, bad, very bad, not so great with that. Also, if I've got small samples, my RMSEA is going to be too large. If I've got low degrees of freedom, also going to be too large, right? So thinking about the types of things that go through and start to impact this index of fit. CFI is an incremental or comparative fit index, okay? What's going on here is this is estimated by taking a look at the fit of the model that you've specified and comparing it against a baseline model. Baseline model, generally referred to as an independence model. This is a model that's saying that there are no associations between any of the variances or any of the variables, right? Is this a reasonable model? Your model isn't saying that there's none of your variables are related to any of their other variables. Not a good model, or sort of not a real reasonable model to compare against, but that's how this is looked at. So basically CFI and TLI, both looking at how much is your model, how much better is your model than a model testing no associations between anything. Okay. Rules of thumb, CFI 0.9-ish, about reasonably good fit, greater than 0.95, close fit. Okay. Now CFI, TLI, these incremental comparative fit indices, criticized because your baseline model isn't plausible. Like it's sort of like, hey, I'm better than something that's really terrible and not realistic actually in the universe. But these are pretty stable. They behave the way they should. They do okay with stuff. But if I get weak associations among my observed variables, CFI and TLIs don't maybe look a little bit lower than they should, because my actual model, if I've got sort of modest correlations between my variables, only looks a little bit better than the model, the comparison model with that says nothing's related to one another, versus a model if I have very, very strong correlations between my stuff, it's giving me more space, right? So something to think about here. TLI, same thing, basically just CFI with a penalty for model complexity. Again, tends to also reject when your n is small, so just being aware of that. And then your SRMR, Okay, this is looking at an absolute fit, looking at your residuals of your covariances. You think about this as roughly equal or telling you the average discrepancy between your observed data and your model implied data. Okay, anything less than 0.1 is generally thought about as favorable. So this is a different fit index that's not derived directly from your chi-square. Okay, and again, this tends to be larger and smaller samples. If I got CFA with categorical variables, SRMR doesn't really sort of behave quite as well as I would have liked. Okay. All right, so take home message with some stuff. Our global fit indices help us determine plausibility of our fit, but it doesn't give us direct evidence that like this is the state of affairs in reality, right? Because there are an infinite number of alternative models that could be fit, and so you need to sort of temper your conclusions based on just your indices of global fit, right? So, thing to remember though with this is our fit tied directly to the estimation of our parameters, right? So if we know how our estimators work, what it's doing, if I get a really garbage model, what I can do is say, all right, what's actually going on in this model? How is it going to go through? Is it being estimated? And sort of start to problem solve what might be happening in my output. Knowing that aspects of my data can start to impact different types of fit indices. There is a massive literature for people who do quant psych stuff. Like this is a whole area, like running different simulations under these conditions, under that conditions. If I combine non-normality in my data with small samples versus large samples versus model complexity, there's just so much stuff to go through and account for. If you're going through and you're running models and you're finding things aren't fitting real well, there's a sea of research out there to go through and start to say, hey, and I do this all the time, like models not fitting real well. What's going on? Well, I've actually have some modest correlations going on in this set. My CFI, everything looks good. My CFI and my TLI are a little bit low. We've got literature saying that might be lower in data that have some modest correlations. Okay, now I can go through and put some context in this. Does it mean that my model's bad? Not necessarily. It means there are just things about my data that don't lend themselves well to estimation with these indices of fit, right? So knowing about this will be very beneficial, both for understanding your own research and replying to reviewers. Always watch out for bright line rules of thumb, right? If your stuff's really low, that's probably not good. But if I got a CFI of 0.94 and my cutoff is 0.95, there's probably not that much of a difference going on there, right? What you want to do is not go through and start screwing around with a model that's fitting okay, pretty good, just to go through and start driving up that thing, because what you're going to get is a bunch of a model with a bunch of bells and whistles that fit the data that you collected, but is not going to be relevant to anything else that anybody ever does in the universe. Okay, so always be thinking about theory, and then remember that your global fit is just one metric. Okay. Looking at localized strain, looking at modification indices, but nothing that you are getting in your output is ever going to trump theory, conceptual stuff, right? Just because your data say that X should be related to Y in this way, if no one else in the universe has ever found this to be true, you have to take that into consideration. So conceptual theoretical stuff should be the main driver for all the decisions that you ever make. So to get after more people in reviews because they just went through and I just like threw on my blinders and started marching ahead and just accepted all fit indices and sort of drew, here's my model. I had a nice model, I had a reason to propose my model. And then I started just adding a bunch of stuff on it to Frankenstein it together to achieve some fit that I thought was good. But what you've done is you produce something that's not going to generalize to anything. You should have stopped 7 steps back, right? Or this model that's really nice, really efficient, does an okay job of fitting my data. But what I really like is this 8-factor model of something because it fits really nice. Well, of course it does, because there are more ways for that data to relate to one another than the more efficient way. And your 8-factor model doesn't make any sense within the context of theory. So just because it fit really well doesn't mean anything. It just means that you made a more complex model that fits better because your data have more options to sort of move around and sort of get from point A to point B. With your 8-factor model, you can't describe what those 8 factors are, how they relate to theory and why they're important. It's a useless model. It's a parlor trick. Cool that you've done that, but it doesn't actually mean anything from a theory research standpoint. Okay, so numbers are good, but numbers aren't the end all be all of this stuff. All right. Thank you, everybody. Questions about anything? Here's references. You go through, I sent that handout out that has stuff on there. Go through, take a look. If there's questions or anything like that, let me know. Happy to help out. Or if you're running models and you're not quite sure why everything is working the way it is, feel free to track me down and find me. I'll sort of help problem solve. It's kind of fun stuff to do. So awesome. All right, thanks everybody. Go Bills! It's the off season. It's a slow burn, and I sort of creep them on there.
Thank you, Josh.
Yeah.
Josh.